me just check for streaming. And we'll get started here. And we're live. Okay. So, all right, welcome to our computer graphics rendering class. And today we're going to talk about textures, frame buffer objects, and render to texture. All right, so I feel like we have a lot of material to cover today, so I'm just going to try and keep it moving because at least I'd like next week to get to shadow mapping, which we really can't understand unless we've had this, how to do textures and all that. So, okay, so for this today, we're going to talk about how do you load texture maps. In other words, how do you utilize them? How do you create frame buffer objects, and then cover rendering to texture maps. And then we'll take a look at the demonstration for that. Okay, so for creating textures, in the slides, I'm going to be posting some documentation that I think is essential reading. So, because I think it's, I want to a little bit avoid this being a tutorial for how to use OpenGL because you may be using other things, but I do want you to read this, these links here, so you can get an idea of how the API works. So, for WebGL, we have that there's two parts. So we have creating texture maps, and then there's using texture maps. Okay, so when it comes to texture maps in the pipeline, let me just go to the board real quick and draw a picture. I need to look for the eraser though. Okay, so texture maps are basically just giant arrays of data, okay, like images, okay? So in WebGL, we only get two kinds, which are 2D texture maps and cube maps, all right? So those are two kinds. Now, if you're using a full featured API, there'll be 1D texture maps, 3D texture maps, rectangle texture maps, a few others, a few different kinds. Oh, arrays. You'll have arrays of texture maps. Okay, so you might want to have like an array. You could kind of consider that to be, like, let's take two-dimensional, for example. A two-dimensional texture map could be considered an array of one-dimensional texture maps, if you think about it. However, sometimes it'd be nice to just have the ability to index your texture map with an integer. So does anybody remember how texture maps are indexed? How do we get into a texture map? What do the coordinates go from? 0 to 1. 0 to 1. Okay? So just as a refresher, let's say we have a texture map, and let's just say that we have, what, say a checker texture. Mess that up a little. Okay, so we have our texture map. This is 0, 0 at the bottom left. All right, 0, 0 at the bottom left. 1, 1 at the top right. Okay, and who remembers what letters we use? U. Well, UV is a common one, but S and T are normally what's used when we're talking OpenGL, or I believe it's the same way with DirectX and a few others. Okay, so ST. So sometimes you'll say UVW for texture maps. You'll see that if you're working with a 3D package, the terminology UVW has been around. That is not the same with APIs though. Most of the time you have ST. Now, can anybody tell me why it's STPQ and not like STR and Q, or just trivia? You don't need to know why, but the reason why is because the other components R, G, B, and A, R is already used, and then we have X, Y, Z, W. So now you know why UVW is not used, because W would conflict with the fact that we were saying the W coordinate belongs. That's the homogeneous coordinate for X, Y, Z. Okay, so this is the one for texture maps. So if you want to make it, now technically when you're writing a shader program, you could say R is X, right? Or S is X. They all map to the same 4 elements, right? If you think of an array as a 4-element array. Okay, they all map to the same thing. However, colors are different to texture coordinates. Texture coordinates are different than 3D coordinates. So as long as you stay consistent with how you use those, it'll help keep you out of trouble. For the same reason that variable naming goes into helping you determine what types are being used and so on. So if you stick with X, Y, Z, for vectors, and X, Y, Z, W for coordinates and so on, that helps keep you out of trouble. Okay, so anyways, texture maps go from 0, 0 to 1, 1. So why would this I guess notation, or not notation, but why would it be more useful to talk about texture coordinates in terms of 0 to 1? Why would we want to do that over using the actual width and height of the texture map? What is gained? I mean, if I had some code here, texture to be, and let's just say map is the name of my uniform, and I say I want to get access to, let's see, 5. I want pixel 5, 5. All right, I want pixel 5, 5 inside my texture map. Well, I mean, what if my texture map was 100 by 100? Is that okay? Yeah. Right. Well, what if now all of a sudden the next generation of GPUs comes out and they have like 10 times more memory than the previous one? I was like, wow, it's 100 by 100 texture maps. They're okay, but people really want the 1,000 by 1,000 textures because they look really, really nice, right? So now you have 1,000 by 1,000 texture map. What is this going to do? What have you hard coded inside your shader? We're asking for pixel 5, 5. And now we're jumping from a 100 by 100 texture map to 1,000 by 1,000. What is 5, 5 now going to access? The same element in our texture map or a different one?
Should be the same element, right?
Well, technically it's the same element, right? But, let's just say you had a picture of a mountain or something.
And
Right.
you can-
And instead of accessing like 5.5, let's just say 5.5 is right there. Now, and let's just say there's like a lake. That's just a sample. But now 5.5 is all the way down here. Okay, so what have we hard coded into this? We like hard coded ourselves into an area that if we just swap the texture map, it no longer represents the same thing. What if our texture map wasn't a picture? What if it was a mathematical function? Okay, let's just say that the shades of gray, let's just say this represented some kind of mathematical function. Okay, because sometimes it's useful. Just pre-calculate a mathematical function. So maybe it's hard to compute, put in a texture map, and now we can look it up. But what happens now is that, what if we want higher resolution on it? We say, now we get more memory. We have hard-coded a pixel value that is no longer valid. So the reason why we go from 0, 0 to 1, 1 is to make sure that when we're mapping our texture map, we can make it any size that we want, and it doesn't change the general algorithm, okay? So if you want pixel 5.5 out of a 100, we instead ask for, say, 0.05, and now no matter what size the texture map is, now we're getting the relative element that we want out of it, okay? So this is one reason we go from 0, 0 to 1, 1. Now we're going to see an issue because how are texture maps stored normally? When we store a bitmap on a computer, where do the coordinates go? Are they at the bottom? Are they at the top? How is a window set up?
From bottom left corner to top right corner. I'm not sure.
The question. Okay, so in other words, if I open like Microsoft Paint, just open up Microsoft Paint here, and let's look at the magnifier. I wonder if that shows up in the, whoa, okay. I might make this just a little bit smaller. Okay, so we have Microsoft Paint. If we put our mouse in here, what happens to the y coordinates?
Increase the load.
Yeah. Why do you think this is? Why do you think this is? It has to do with the way that you address into the memory buffer. Okay, so so I'll erase this real quick. So your memory buffer, right? Let's say we have a two-dimensional buffer. It's got a certain width, a certain height. Okay, and this is our memory. Okay. And let's just say we're trying to store this texture map, and let's just make it a one channel, it's either on or off kind of deal. So this would be 1, 0, 1, 0, 0, 1, 0, 1, 1, 0. Okay? So if we were storing this texture map in memory, then we would basically say that y times the width plus x equals our address. Okay, so that's our address in memory. So if we want 0, 0, element 0, 0 in memory, then that's the width is 4, so 0 times 4 plus 0 equals 0. So that's our first element. And then let's say we want the first row and the first pixel. That's going to be 5. Okay, so this was the first one. 1, 2, 3, 4, 5. Over here. So we wanted that one. And so the reason why they're laid out in memory, normally for a bitmap, is that you're thinking, okay, the top part of my image buffer starts all the way over here. So y has historically for bitmaps gone down. So positive y means, or as you increase y, the further down the image you go. And that's normal for any kind of image drawing software. That's normal. However, it's the other way when we're talking about texture coordinates. But why do you think texture coordinates are backwards? In other words, the memory buffer for this texture map is going to start here. So this would be 0, 1, 0, 1, 1, 0, 1, 0, 0, 1, 0, 1, 1, 0, 1, 0. But we start over here. So for what reason do you think that the texture coordinates would be increasing going up? What's kind of unique about computer graphics, all the math calculations we've been doing? Let's just say you had your niece or nephew over and they're saying, I'm learning about graphing in math. We're doing function, we're drawing lines, okay? And you might say, okay, well, let's go ahead and get some graph paper out. How are you going to draw that out on the paper? Right, Cartesian coordinates, right? We're thinking, okay, yeah, positive y goes this way, x goes this way, right? This is very common, right? When we do mathematical calculations in computer graphics, we treat it like it's like a math equation, okay? Now, this, where we go down, that comes from more computer science. I need to represent an image buffer. So it makes sense to be able to say that the top right or the top left of the screen is the first element in memory. Okay, first element in memory. So this issue is going to crop up because when you load up a texture map, what direction is it stored in? Yeah, if we're loading an image file up from the disk, what direction is it stored?
The regular mathematical
No. It goes down because it's a bitmap that we're going to draw on the screen. So bitmaps go down because we're starting top left of the screen, starts in the corner up here, going left to right, left to right, left to right, all the way down. Okay? But in a shader, when we're using the Cartesian coordinate system, STPQ, we're going, or UVW, UV coordinates are defined from a mathematical frame of reference, where 0, 0 represents the origin, and 1, 1 represents the other corner. Okay? So, it's kind of confusing to say, and let's just think about it. Let's say we're going to tile an image. We're going to tile an image. In other words, I mean, what happens if we decide that we're going to have texture coordinates, let's say 1.5, 2.7. Where is this texture coordinate? If we're going 0 to 1, 1, where is this texture coordinate at? What do we do with that? We could clamp it. We could say, well, yeah, no way, you can't go outside the texture map. That's not allowed. Okay, so clamp is one thing we could do. And we could say that actually is 1, 1. So when we look up inside our texture map, we're only going to be we're going to get this one. This, okay? That is one strategy. What's another strategy? What if we have a pattern in there? Is that going to make sense? We want to fill a polygon with a pattern. Maybe it's like stripes, checkerboards, houndstooth, whatever you want. What do you think? Does it make sense to be able to allow texture coordinates to go beyond, to repeat maybe? We want to repeat. So in other words, let's just say we're doing this one, 1.5. So normally going horizontally, right? You go, that's 1, and then maybe go here, 0.5. In other words, just as many times as it wants to wrap, just let it repeat over and over again. And that one's not too bad, right? Because we could just say, well, you can just take the fractional part of the coordinate and then just say, well, that's the new texture coordinates, because those always go from 0 to 1. That always stays in that range. Just take the fractional part. So 2.7, where's 2.7 going to get us? About over here somewhere. So you can repeat, right? Maybe we want to repeat. In which case, 0.5 to 0.7. Okay. What other? We're going to look at a few others. These are probably the two most important ones: clamp and repeat. Because sometimes you don't want the texture map to be, what if you had because you also are fighting that numerical precision, okay? So you're fighting numerical precision, and what if you have like 1.01, or minus 0.99, or 0.1, right? Sometimes you get these issues where your calculation doesn't come out exactly what you want. So if you had repeat turned on, then what happens to 1.01? Yeah, 0.01, so you end up getting black instead of white, or actually not black. So you end up getting white instead of black, like you were expecting on the checkerboard. So clamped would be like, oh yeah, no, we're not going past that one, and we're not going below, because if we had minus 0.01, what happens to our wrap? We'd go all the way to the other side and start working our way backwards. Okay, so there's a few different ways we'd like to do it. Now let's see how that would be confusing if we use the Cartesian coordinate system, okay? But we had our textures going the other way. In other words, this was 0 and that was 1. Let's see how that might be confusing. So draw our Cartesian coordinate here. There's our texture. Now we want to read row 0. Okay, well that's over here. Okay, and now we want to read 0.5. Okay, that's over here. 0.25. That's over here. Let's just say we want to then measure. We're doing like repeat, right? So we measure 0.01. Now we're back up here. It's got this. That is really confusing to tell you how do you do that calculation that way, right? I think it's confusing. Okay, but if everything starts off here, then it's easy to kind of do those calculations. Where am I in the texture? So we're gonna actually take a look at that. Just a second. All right. Any questions so far?
So the reading from top left corner to bottom right, was there any particular reason besides that up there? Was it just for simplicity's sake?
It's a simplicity's sake when you're doing the memory, accessing the memory. Okay. And same thing for if you're addressing text columns and rows and columns, So you just kind of say 0, 0 is up at the top of the screen because that's where you start writing. And then it goes down and you just scroll up. So thinking of it in terms of a piece of paper where you start writing at, it makes sense to store your memory at the very top. Otherwise, you're thinking about storing memory on the very bottom. And then what if you want to scroll up? You know, your whole screen shifts up. What happens? Then you're like, okay, I got to shift the whole memory buffer up to put a new line on the bottom. Now, is that making anybody uncomfortable? Like thinking how that does it? It's not simple. Okay, it's not simple at all. So images, stored from the top because it's easier to keep appending to a memory buffer than it is to shift an entire memory buffer up to add another line. And then what if your line is arbitrary width? You know, it's a lot easier to reinterpret that from a computer science standpoint than it is to do the other way. However, mathematically, let's just say that you wanted to rotate your texture. You want to rotate your texture map. In other words, you say whatever my ST coordinates are, I want to rotate it. Okay, so you could just apply a two-dimensional you could just apply a transformation to those coordinates, and then you can just rotate it. All right, pretty cool. We're gonna play around with texture maps in just a few minutes, okay? But the first part, right? We have to figure out how do you create textures. Okay, so the general idea here is we're creating a texture. Then you, just like programs, like shader programs, you have to bind, you have to use the programs, you have to basically say, hey WebGL, here's what I currently am using. So you would, after you create your texture, then you bind your texture, and you normally bind it to a two-dimensional texture or a cube texture. Now whatever you bind it to the first time, that's what it becomes for the rest of the lifetime of that object. Okay, okay, then after you've bound the texture object, we have basically said now it's going to be a two-dimensional texture or a cube map texture, but it doesn't have any data associated with it. So the next part is setting the image data, which we could use text image 2D. All right. Now, if you're using a fancy version of OpenGL, then you get like text image 1D, text image 3D. You have a few different ones that you can do. Then our texture properties. Some of these are easier to explain when we look at it than it is to explain up on the screen. Suffice it to say that, so we have, these are the 4 parameters that we can really adjust in WebGL. So the minification filter, so how do we sample pixels when it becomes small? The magnification filter, so what happens when it gets bigger? And we kind of looked at that. Remember we were talking about the sparkly textures a little while back. We looked at the Game Descent and we kind of zoomed out and we're like, we got that sparkly effect because we don't know which texture we should get. So looking over here, if we're supposed to, we were talking about sampling, okay? And if this, let's just say that this texture was being sampled 1 pixel, you had an object zoomed out so far that technically this whole texture should be represented by that 1 pixel, then it's a matter of, well, which one do you pick? And you have 0 and 1 in there, so if you pick 1 off chance and the next frame you pick 0, the next frame you pick 0, and then the next frame you pick 1, then you get this flickering effect that happens, okay? Because you can't decide which one you should get. So we're going to look at that, what happens when you minify something, make it smaller, and magnify it. Okay, so then we have our wrap, and we were just talking about that. There's 2 strategies. We could clamp to the edge, so we can say, you know, no, we don't want to go past because our texture doesn't tile. And we could do repeat. So if we have patterns and we want to like spread across a whole surface, we can easily do that. Okay, so after we've set the properties, set the image data, then we can go right ahead and unbind it. Okay, so now we want to use textures. Now we want to use them. So we've created them. Now we want to use them. So first thing we have to think about is that the texture, the way that the pipeline is set up, is we have a vertex shader, we have a fragment shader. Okay, and we know that we can set uniforms. Uniforms are those variables that are constant across those shaders. Okay, but we also have a texture unit. And one way to think of a texture unit is, let's just say it's the minimum specification for WebGL. 1, 2, 3, 4, 5, 6, 7. We minimally have 8 texture units. In other words, we could attach up to 8 texture maps and then access those in either the vertex shader or the fragment shader. Okay, so maybe 0. 0 is normally like the default texture. So sometimes it's useful to set like your diffuse texture map in there. So I'll just put diffuse. Diffuse is basically a matter of absorption. If you remember from the BRDF, right? We have that constant BRDF is 1 over pi times rho. The rho is how much is absorbed. So in other words, that blue, for the sake of just thinking of red, green, and blue, that blue chair over there, one way to think of it is it reflects blue light. That means it absorbs red and green and all the other colors. It only reflects the blue. Okay, so normally we put our diffuse texture in there. In other words, what's the albedo? What does it reflect? Okay, so that would be like the wall, a wood texture, you know, something like that. So we have up to 8 of these, and we have our uniforms. So maybe we're going to call this map KD. In other words, this is our diffuse texture. Okay, and so we can set this uniform up. If you noticed on the bottom of the slide, right, we're going to configure the shader program uniform. So in the shader, we have a variable. Over here, I'm going to call it map KD, but in there it's called my texture. And we could say, first we need to find out what's the location of this uniform. And then we basically say, what unit is the texture in? So if I have bound my texture to a different unit, like this one, we would say set map KD to 0. In other words, use unit 0 for the texture. Okay? And maybe we have a specular map. Maybe that's in 1. Okay, and maybe we have a map for normals. Maybe that's in texture unit 2. Okay, so we basically use any one of these 8, map it to any one of our uniforms, and then we could like bring in all this extra data that applies to the surface of a polygon. All right, and then when we draw our triangle, you know, we have these texture coordinates. Maybe this is 0, 0, and this is 1, 1, and this is 1, 0. Okay, so you know, if this was the checkerboard texture, then I could maybe imagine something like this. Just taking a guess over here, where we're basically just mapping this texture map onto this surface. Okay. Okay, so we have 8 texture units, so we can use gl.setActiveTexture, and so gl.texture0, gl.texture1, texture2. We're guaranteed at least 8. Most platforms support way more than that nowadays. I remember when it was just 1. And you were like lucky to get 2, and that was like, yes, 2. I can put, you know, because then otherwise what you're doing is you have to render several different layers, right? So having a minimum of 8, man, that's nice. Okay, that's pretty cool. Okay, and then your target. So you have to remember what target you used last time. Most of the time you're just using texture 2D anyway, but there is texture cube map. All right, now, okay, so that's using textures. Okay, so we got to create them, then we can use them, and this is how you more or less how the shaders are using these maps. Okay, and the vertex shader, I guess we could add an extra. We have a uniform, and it's called a sampler to me. So maybe noise is mapped over here to 3. Maybe we have some other extra data. So maybe we could perturb or you know, modify our what is it? 3D locations by whatever is inside this noise map. That could be fun. Okay, so the next step. Okay, we have texture maps, but maybe it would be nice to render to a texture map. To a texture map. All right. So in other words, it's not an easy thing to just draw. But think about it this way. If I wanted to use the image that I'm drawing in my frame in my viewport, or maybe I want to do something special like a reflection, or I want to do. We're going to talk about shadows next week, but let's use this example of. Let me see if I have. I want to see if I have an image of, might be under research. I want to find Alot Watt. Hopefully it's just not on my other computer at home. I'm either going to get lucky or I'm not. I'm thinking I'm not going to get lucky. Okay, maybe I get lucky on the internet.
For a second, I thought you were looking at Alot Watts.
Oh. Yeah, not. It's this book. This is one of my favorite 3D graphics books. Maybe I'll get some lucky and somebody will have. Oh, it's on archive.org. Cool. see other formats. I don't think I'm gonna. That's okay. Let's just say that our use case is that we want to render a reflection of something. In other words, we have we might have a 3D scene here where we got a few objects. Funny. Wow. Okay. A teapot. Okay. But this is not the scene we're looking at. This is the computer monitor. That's what we want to render, with that image rotating inside of it. Okay? So, it's sometimes useful to be able to render to an off-screen buffer. In other words, we're going to render to a buffer, and then we'll reuse it later on for something else. And normally we'll call it render to texture. Okay? But we can also just render to a straight frame buffer, which is almost acts just like the screen, except it's not on screen. Okay? So some of the applications could be, we want to render a gbuffer when we were talking about deferred rendering, right? So render stuff so that later on we could do all the lighting illumination. Shadow maps, so that's what we're talking about next week. Reflections, all sorts of different kinds of things we might want to do. So frame buffer objects is the ticket to be able to do that. So we want to render a 3D image that we can reuse later. Very useful thing to do. So in order to do that, we can render to a texture map. And the general way that we do this is we create a frame buffer object. We create our textures and initialize them with empty data. Then we attach them to the frame buffers, which there's two. There's the color attachment, which is the red, green, and blue, right, our color. And then a depth attachment, which is our Z buffer. Okay, and once we've done that to the frame buffer, then when we're going to go render to it, then we bind the frame buffer object, then we render just like normal, and then we unbind. Now, the reason why we unbind the frame buffer object is now we can draw back to the main screen, for one. Two, we want to use those texture maps that we attach to the frame buffer as an input, right, to our shader. Okay, because you can't, with a frame buffer, you can't have a loop. You can't be writing to the same texture you want to use to read from. That doesn't, that doesn't make any sense. It's like, it's like trying to cook a recipe with the final output. It's like, that doesn't make any sense. You're like, here's, you're trying to make like a banana cream pie. Okay, so first you need to make the banana cream, and then you make the pie, right? You put the banana cream in the pie. So this would be like saying you don't have the banana cream yet. You're making the banana cream while you're trying to do the pie at the same time. It's like, well, you can't do that until you got the banana cream first. It's like trying to ask for something in the future. It's going to turn out to be a mess. Okay, so you have to make sure that you're not using a texture you're writing to the same time you're trying to read from it. It won't let you do that. And because of that, yeah, frame buffer objects are kind of tricky. So my recommendation here is please read the documentation, okay? But then see fx.fbo.ts for implementation details. Okay, so inside the libxor library, just dig down in the source code, you'll find this fx.fbo.ts, and that has all the details on how to do it practically. Okay, and for texture maps, kind of same idea. There's some texture stuff inside the. All right. Okay, so we're going to. Any questions so far? What do we? If we want to render an image to an off-screen buffer, then what do we use to do that? A frame buffer object. Okay, so if we want to render to an off-screen buffer, then what do we use? Frame buffer object. Okay, and if we want to use an image inside of our shaders, what kind of object do we use? A texture object. Texture object, okay? So we use texture objects if we want to use images inside our 3D program, and then we use frame buffer objects if we want to render to an off-screen buffer. Okay, so we're going to take a quick